So hope all of you already got so many information about cloud computing. But still, the title of my talk is Cloud Computing Overview and Research Challenges. So I will briefly discuss some of the points of cloud computing, and then we'll jump to the research challenges, and we'll focus on a particular challenge. If you have any questions regarding my talk on any particular slide, you can interrupt me and you can ask me whenever, wherever you want. So I can start. So as I told you that you probably know what is cloud computing. Still, I would like to start with this concept of what is cloud computing and how we can perceive this technology. So there are several definitions you may find. There are several definitions are already available online, and we all pretty much aware about this technology, cloud computing, right? We don't need to know the theory in details, but we all are using cloud computing nowadays because we all are using smartphone, right? And when we are using smartphone, with our smartphone, we are getting this facility of cloud. You can pick any smartphone, Android or iOS or any kind of smartphone. You will get some sort of cloud facility there, which basically tied with your smartphone, like the storage facility. Sometimes we are getting a lot of data through the WhatsApp or the mails or the pictures that we are taking through our smartphones. And usually our smartphones are not always that resourceful in terms of storage to store all this data or the images or the documents. So sometimes or most of the times the smartphones are tied with some cloud services. And they are providing this cloud storage platform to us, and with our knowledge, they are pushing some of these images and documents to the cloud, right? And whenever we need those information, data or images, we can download that from the cloud. And essentially, we don't need to keep all this information, images, documents, files in the phone itself. So we don't need to know about the theory behind this cloud, right? But we are using it. And not only we, almost if you think about your parents or some older people, those who are using smartphone, they also they are also using this facility. They probably don't need to know the theory or the concept behind this, but as we are what we can say the student of computer science, and we working practitioners of computer science field, we should know the technology behind that. And from that perspective, if you go by this definition given by the NIST, this definition is given by the NIST. NIST.gov, and according to this definition, it is a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources. Here, when we are thinking about the resources, these resources are nothing but the networks, servers, storage, applications, and services. The services could be anything, any type of services that can be rapidly provisioned. This is a very interesting concept behind the cloud computing, that is provisioning, and released with minimal management effort or service provider interaction. So you just pick any example or any example scenario when you are using this cloud platform. Just take this example of when you are using cloud services through your phone for storing your images or for storing your photographs that you clicked through your smartphone. What you're doing actually, you're taking a particular service, right? And you are taking the storage facility, and the storage facility is not available in your handheld device. It is somewhere remotely available. So all these things, all these resources are visualized as a shared pool of configurable computing, shared. So why it is called shared? Because we all are using all the users connected to that services can share that resources through that pool. And it's very much configurable. Configurable means according to your required, according to your demand, you can expand it, you can reduce it. For example, just assume an application scenario when you are getting this storage of say 16 GB. Okay, but 16 GB is not sufficient for you, and you want to expand it. So you can buy more storage from that cloud service provider. You can expand it up to say 64 GB. So that expansion or providing this facility of expansion, providing this facility of increasing the resource power or decreasing it is known as this concept of configurable computing. And everything here is on demand. Whenever you need, you can get that service. So it's an on-demand thing. Now, one very interesting point that I told you, that the provisioning. Provisioning is a very important feature. Sometimes resources are over-provisioned, sometimes resources are under-provisioned. To explain this concept, let me give you one example. Suppose there is a resource, say R, and this is your demand. You need the resource R. But when you're placing this resource request, and you for the budget purpose, suppose you're placing the request demand, say R minus. So essentially, say R minus is less than R. And another scenario, when your requirement is R, getting say R plus. So when you're getting R plus, that is R plus is greater than R. So this is one case where the resource that you are getting is more than what you need, because here your need is R and you are getting R plus. This situation is called over provisioning. This situation is called over provisioning. Just with me, because I'm using this pen utility and the handwriting is not very good. So this situation is called over provisioning. And this is the another situation where your demand is R, but you are getting R minus. This particular situation is known as under provisioning. So these two things are there in terms of provisioning in cloud computing. So when you're defining cloud computing, these are some important or essential characteristics which are using for this concept of cloud computing. So as I told you, there will be this concept of different essential characteristics in terms of defining cloud computing. One is the on-demand self-service. Then there is this broad network access that must be there. Otherwise, it's not possible to access these resources from the remote location. Then all the resources are actually pooled together. So it's a kind of a resource pooling, which is shared by the users or the consumers, those who are accessing that resources. There's this functionality of rapid elasticity in terms of providing more resources, or if required, you can decrease the demand, you can take less number of resources. So this elasticity, rapid elasticity is another very essential characteristics of cloud computing. And finally, it's a measured service. That means this particular concept of cloud is pay and use model, right? Pay as you use. So you have to measure the service, how much service you have acquired, or how much service you are taking from that service provider. That should be measured, and based on that measured service or measured usage, you have to pay. So that's why it is called pay and use model. So these are some of the things that you should know from the definition point of view of cloud computing. Next, if I move the service models, I am sure that you all know about the service models, but before going to discuss more, let me give you a very simple example of how to perceive the service models. Let's take an example. Suppose you want to start a business, and for that you did some research on the requirement of or the infrastructure requirement, etc. So this is one particular plot where it is showing the infrastructure cost to set up your business in respect to time. Okay, and based on your historical data or based on your research, suppose you come some model which is shown by this dotted arrow line. This particular line is that the infrastructure cost will increase with time, and this nature of this increase is very linear. Okay, with time it will increase, and it's a very simple linear model. But in reality, the situation probably is not like that linear. So here you can see there is a red line curve. Sorry, there is a red line curve here. This particular curve. This particular curve is showing the actual demand. Actual demand means it's not following any linear nature, but sometimes it may increase, sometimes it may decrease, sometimes it may go with this budget. But when it is above the existing infrastructure, that means in this period of time you fail to provide the service because you don't have that infrastructure, because your infrastructure is bounded by this dotted line. Similarly, when it is below the dotted line, that means this portion, in this portion you are actually getting the service, but you have invested some cost or some money there which is of no use because the demand is not that high. Here the demand is denoted by this dotted arrow line. Now, what should be the best solution to address this problem? The best solution is if you have some environment where you can automatically scale up and scale down the infrastructure cost, which is shown here by this green line, green curve. So according to this green curve, when there is this demand high, you can put more cost for building better infrastructure. When the demand is low, like here, you can down the cost and you can go less than infrastructure. But in reality it is not possible, because if you want to buy something or in on-premise solution, you have to invest that cost and you have to get the hold of that infrastructure, right? So if it is if you follow this dotted blue line, sometimes during some period of time you have invested a huge capital there and improved the infrastructure for a period of time or for addressing that issue, and you have to go with this capital cost like here. So that is not a very good solution here. Or if you go with a smaller time period of time as shown by this green dotted line, probably again you have to go with this loss, right? So what is the best solution? The best solution is here shown by this automated scaling. That means the green arrow, green curve, which goes up and goes down according to the demand. But in reality or on premise solution, it's not possible to have this type of solution. So what next? Cloud environment provides this different type of service models. In this service models, it's actually denoted by X as. So it's denoted by X as service. This X could be anything. Here X could be infrastructure, like as shown here. X could be platform, or X could be software. So infrastructure as a service, platform as a service, software as a service. Nowadays there are different type of solutions are available where X could be sensor as a service, where X could be data analysis as a service, where X could be anything. You have to think about a service that you want to provide in this cloud platform, and you can think about that as X here. Now, how these three models, this infrastructure, platform, and software as a service, how these three things are different from the on-premise. So if you think about the different responsibilities of building a cloud platform, you need to think about these stacks, which are shown over here in this blocks. We just started with the networking, then there is a storage, then servers, then virtualization, operating system, middleware, runtime environment, and then finally comes this data and applications. So in on-premise solution, just like discussed in this particular example, all these things are under the control of the subscriber. All these things are responsibility of the subscriber or the consumer. So if you start your business and if you go with this on-premise solution, you have to think about all these three, all these layers, right? So which is not a very beneficial solution, as we discussed during this explanation of this particular diagram. Now, cloud provides different type of service models. In infrastructure as a service, this four layers, starting from the networking, storage, servers, and virtualization, these will be the responsibility of the service provider. So if you take this cloud service from, say, AWS, if you take the service from AWS or maybe from the Google service provider or Azure or Heroku or any service provider, the service provider will take the responsibility of this part. And the rest of the layers, that means starting from the operating system, middleware, runtime, data application, these will be the responsibility of consumer. Similarly, in platform as a service, the more layers, like starting from network to the runtime environment, all this will be taken care by the service provider, where only these two top layers, that means the application and data, will be the responsibility of the consumer. However, in software as a service, all these things, starting from the networking to the application, the whole thing will be under the control of service provider. So the consumer and or the user don't need to bother much, don't need to bother anything about that, and they will get only the services. So if you think about the AWS EC2 platform, that is an infrastructure as a service. If you think about the platform as a service, then Heroku provide different type of platform as a service. AWS and Google Cloud Platform, GCP, they are also provide different type of platform as a service, where you need to bother about the application and data part only. And software as a service, there are a huge number of applications available, and we are using these applications in our day-to-day life, starting from the Gmail, Facebook, any online social media, or think about any software that you are using as a cloud, are actually example of software as a service. Next, the deployment models. In deployment models, different type of deployment models are there. The first one is the private cloud. Private cloud means that could be on-premise or off-premise, but operated solely for a single organization. For example, if you think about, say, the Jadavpur University, and in Jadavpur University, we have a cloud environment, and that is a very private cloud environment. Only the students and the faculty members of this university can get the access of that, and that's why it is called private cloud, because outside from the Jadavpur University, you cannot access this cloud. So this is an example of private cloud. Then there is this community cloud. In the community cloud, it's again could be on-premise or off-premise, but the beauty of community cloud is it can be shared by several other users that have a common purpose. That means if it is possible to access the university cloud platform with outside from the university campus, maybe through some other institute, maybe through some other college, then it will be called as a community cloud. Then there is this concept of public cloud, where this public cloud is available to the general public. For example, AWS Cloud Platform, Amazon Web Service Cloud Platform, or Google Cloud Platform, or Heroku, Azure. So these are some cloud platforms which are available for public and owned by a single organization. Like AWS is owned by Amazon. Google Cloud Platform is owned by Google. Heroku is owned by some single organization. So the single organization is responsible for selling the cloud services, and public who can access that services from that organization. Then comes this hybrid cloud concept. Hybrid cloud is basically a combination of two or more private or community or public clouds. So hybrid cloud means it's not like a pure public cloud, or it's not like a pure private cloud or a pure community. The mixture of private, community, and public cloud is known as hybrid cloud. Okay. So next concept is the virtualization. This is a very important concept of cloud environment, and let's discuss about that. So this is one picture which is depicting some resources, the hardware resources, which is shown over here. So in this hardware resources, you can see the CPU, central processing unit, you can see the memory, you can see the network interface card and disk. So on top of this hardware resources, there is one operating system. Here, you can see there is only one operating system, and this hardware and this operating system, these two things are tightly coupled with each other. These two things are tightly coupled with each other. And on top of this, that means the hardware and software, which is tightly coupled over here, you can see there is this application layer. This app, if something goes wrong with this application, that will affect all the resources over here. And resources, you can if you think about, as there is only one application running over this hardware and software stack, that this application is only utilizing these resources, but the available resources may have more power, or they may have able to provide services to more than one application. But in this situation, it is not the case, and you can say that resources are not properly utilized here. So in this scenario, there is a high chance the resources are not properly utilized and they are underutilized. So this is actually a problem with the standalone systems, with the system without virtualization. Now, to address this issue, there is this concept of virtualization and comes into the picture. So to address this issue of resource underutilization, what we can think about a virtualization layer on top of the hardware layer. So this is the hardware layer, which is the same as the previous one. And on top of this hardware layer, there is one virtualization layer. So what is the main responsibility of this virtualization layer? This virtualization layer provides the virtual view of these resources. They are providing different type of instances of machines to the environment. So you can see that this is one instance of the same resources here, and you can see another instance of this hardware resources here, right? So when you have the separate instances of resources, hardware resources, you can build a separate operating system on top of this. So this hardware resource instance with this operating system, they can build a virtual machine. So this whole thing is known as a virtual machine. Similarly, here you can see with this instance of resources, there is another layer of operating system, and you will get another virtual machine here. Okay. So on top of this virtual machine, multiple applications can run. Here, 3 applications are running. Here, another 3 applications are running. So they are utilizing the same resources, right? So the resource utilization is much better in this scenario. So here, the machine view to the operating system is independent of the hardware. Multiple OS, isolated applications can run over this environment. And here it is possible to safely multiplex resources across different virtual machines. Now, for this virtualization, different type of approaches are there. The first approach is the virtualization with software. So, if you look at this layered architecture, what you can see, there is this hardware layer. On top of this hardware layer, there is the host operating system. So, these two things are the physical part of the system. On top of this hardware and host operating system, you can place a virtual machine manager or VMM. So what is the responsibility of this VMM? This VMM will provide the different virtual machine instances over here. So these virtual machines are using this hardware and this operating system. And virtual machine is providing different, virtual machine manager is actually providing multiplexing the resources in these three different virtual machines. So when you get this three different virtual machines or machine instances, you can install your own guest operating system over here. So separate guest operating system can be installed in different virtual machines. As you can see that here you have guest operating system Windows, here you may have guest operating system Linux, but all these things, all these virtual machines are using the same host and hardware, the same. And here you may have guest operating system VMware. On top of this, VM, you can run separate applications. So this is how you can visualize the virtualization architecture in terms of software. Another approach is virtualization architecture in terms of hardware. So here, as is an hardware approach, you can see only the hardware is part of the physical system. So it is the part of the physical system. And in the virtual mode, what you have the host OS along with the virtualization layer. So this combined layer is actually acting as a virtual machine manager here. And again, it is providing separate virtual machine for that. And rest of the actions or rest of the working procedure is same as the previous one. Now, this virtualization layer is also known as hypervisor. This is also known as hypervisor. So the virtualization layer, which is known as hypervisor, which is creating different type of virtual machines. In different virtual machine instances, you can install different operating systems, and in different virtual machines, you can run your applications also. Okay. So, so to address this research issue for resource utilization, there are different type of solution approaches. One such type of solution is load balancing. Then comes the fault tolerance and power or energy management, server upgradation, and server consolidation. So these are some of the challenges associated with resource utilization. Sometimes we have to do the load balancing to make the environment more fault tolerant. Sometimes we have to we need some solutions which is very energy efficient. For energy efficient solution, we may prefer load balancing, or sometimes there may require some server upgradation. If server upgradation is required, you may need to because server upgradation is very important for making a system fault tolerant one. And then there is this concept of server consolidation. So these are some approaches which are majorly used for handling this resource utilization problem. And in all these approaches, whatever listed over here, starting from the load balancing, fault tolerance, energy management, or server upgradation and server consolidation, in all these approaches, a very common solution is migration or VM migration. So we'll discuss about the VM migration because it's very difficult to cover all the challenges and all the solution approaches in one lecture of 1 hour 30 minutes duration. So I will focus on this migration part only. So what is this VM migration exactly? To explain this concept, let's take the help of this particular picture. We can see that there are two computers, A and B. Okay, there is one question. From where I will get this question? Okay. Is the load balancing is the part of distributing system? Yes, load balancing is part of the distributed system. I'm explaining that. If any question, you can ask me also. Wait. So if you take this example where you have, say, two computers, A and B, and assume that in system A, 3 virtual machines are running, and in system B, only 1 virtual machine is running. So looking at this solution, what you can say that the load in A and B are not balanced, right? A is heavily loaded, where B is not that heavily loaded, lightly loaded, right? To make this situation a load balancing one, what you can do, you can simply migrate one VM from A to B like this. So the solution will be something like that, when A will have 2 VMs here and B will have another 2 VMs. So this situation is a much more balanced situation. So this one is the balanced situation. So this is one scenario of load balancing. Another scenario is, just take another example, when there are, say, three systems, A, B, and C. In all these 3 computers, or in 3 physical systems, only 1 VM is running, right? So you can think from the balancing perspective that this solution is a balanced solution when all the 3 systems are running 1 VMs. But if you think this from the energy management point of view or energy consumption point of view, this solution is not a very good solution, because for running the 3 VMs, you have to keep on these 3 physical systems, while one physical system is good enough to run these 3 VM instances. So this is not a very good solution from the energy perspective, but it's load balance. So what you can do to make it an energy efficient solution, you can migrate this VMs from this physical machines to one physical machines like this. So here, this solution is a very good solution from the energy perspective. So this is how we can address different issues related with the resource utilization. Here we are thinking about the load balancing, when we are trying to balance the resources of or the loads of this physical systems. And in this approach, in the second scenario, we are trying to make it more energy efficient. And in both the situations, in both the scenarios, we have to take the help of VM migration, where VM migration is the solution for addressing these resource challenges. The next concept is the server consolidation. What is server consolidation? If you think about server consolidation, it's one of the benefits of virtualization. And using this concept, what we can do, we can increase the resource utilization, and that will also reduce the electric power consumption cost. As shown in the previous example, there are two important factors. One is to increase the resource utilization, and another is to reduce the electric power consumption. To understand this concept, let's take this example scenario. So here there are 4 servers running, and the server usage are given over here. The first server, for the first server, usage is 55%. For the second server, its usage is 70%. For the third server, its usage is 40%. And for the fourth server, its usage is 20%. So how, next we have to think about how server consolidation may help here to improve the situation. Here, if you can see, if you if you migrate the VM running in this server, as the usage is 20% only to this server, you can easily do it, because here the 30% resource is not utilized, but here the requirement is only 20%. So what you can do, you can migrate this virtual machine from this server to this one, and simply make this server off, like here. Similarly, for this one, you can migrate it to this one. So here you can see the server, the VM which was running in this particular server was migrated to this one, and the VM running in this one is migrated to this one. And after doing that, what you can do, you can simply switch off these servers. And after switching off these servers, what you are achieving is the reduced electric power consumption. Now you have this thing. And on the other hand, as you have already migrated the VMs over here, so you are actually increasing the resource utilization of these two servers. So this is the concept of server consolidation. Now, there are different approaches for doing this server consolidation, and these approaches are mainly static consolidation and dynamic consolidation. Static consolidation means when the utilization of this peak load demand, you have idea about this peak load demand, virtual machines does not overload. So these two things are maintained in static consolidation. And in static consolidation, virtual machines stay in the same physical service during the whole lifetime. They are not migrated from any other servers. So as it is called the static, it's supposed to stay in the same physical service during the whole lifetime. However, it can also lead to the idleness problem because the workloads can present variable demand patterns. So if the situation is like variable demand patterns, it is not possible to address it with the help of static consolidation. Another approach is dynamic consolidation. In dynamic consolidation, since the demand is dynamically changes, and virtual machine capacities according to the current workload demand need to be increased or decreased. So the dynamic consolidation is the best solution to address that environment. In dynamic consolidation, what you can do, you can pull out the physical servers from an overloaded state and turn off or on the physical servers as discussed in the previous examples. So if we compare the server consolidation techniques, you can see that static technique, it's useful if the demand is consistent, but dynamic technique is good for both the situation when the demand is consistent or demand is dynamic. Here the VM and PM mapping is not changed for a long period of time in static, but in dynamic, VM and PM mapping changes several times to accommodate the demands, because here the demand is not fixed. The demand can change with time. In static technique, there is this concept of resource over provisioning, because you have to think about the peak load, and based on that peak load, you get that upper bound. And based on that upper bound, you are assigning the VM. So it is basically over provisioning scenario. But in dynamic technique, it is more balanced, because based on the demand, you are actually doing the server consolidation. So you don't need to think about the over provisioning scenario, because over provisioning will not appear here. It will handle the situation based on the demand and will do the consolidation. Then the workload pre-predicted here in static technique. As I told you, you need to have some idea about the peak load demand, right? However, in dynamic technique, it's more real-time predictions. In static of resources, when PM are underutilized, that we have seen in the previous example also. If the PM physical machines are underutilized, there will be the wasting of resources, and resource utilization will be very poor. However, in dynamic technique, it's better managed, because you have this option of load balancing, or you can dynamically address the things. And static technique, there is no migration required, because the VMs will be placed at and they will stay in the same physical machine for the entire lifetime. But in dynamic technique, it is not the case. The VMs can move from one PM to another PM based on the requirement. And for moving VM from one machine to another machine, migration is the key. So as a whole, static technique is very easy to manage, but not very efficient. But dynamic technique is a bit complicated, but very efficient, and it has a good performance over the static technique. So as you can see, that server consolidation using static technique is not very effective in demands, but a dynamic technique is effective, but it has its own research challenges. So let me give you one example of VM migration and destination PM selection. So you can see that in this figure, say here, suppose there are 3 virtual machines. There are actually 3 physical machines, PM1, PM2, and PM3. And 3 virtual physical machines are there, and this is showing the CPU and memory utilization. And there is another physical machine, PM4. In PM4, 3 virtual machines are running, VM1, VM2, and VM3. And by looking at the VM1, what you can see that the CPU is overutilized here, but the memory is not overutilized. But here in PM1, CPU is underutilized. Here the CPU is underutilized, and memory is not overutilized, but it has some capacity. So if you can look at the VM1, which is running over PM4, what you can do, you can simply migrate VM1 to PM1, because PM1 physical machine 1 has low consumption, right? And VM1 has high consumption. So you can migrate VM1 from PM4 to the PM1. So this is how you can decide upon which VM machine, VM instance will be migrated to which particular destination physical machine. So here, just at looking at the load of the CPU and memory utilization, you can decide that the VM1 should be migrated among this VM1, VM2, and VM3, which were running in physical machine 4, and the destination physical machine should be PM1, because you can see that in physical machine 1, the CPU is not overutilized, it is underutilized over here, and memory is overutilized, which is simply the inverse of the VM1 requirement. So VM1 can fit better with the PM1. So there are some trade-off situation also. Let me explain that. Here you can see that there is 3 machines running, M1, M2, and M3. These are the physical machines. Okay, but M3 is currently off because no VM is running on M3. But in M1, 2 VMs are running, VM1 and VM3. And in M2, there's 1 virtual machine running, that is VM2. Now, after some period of time, suppose the demand of VM3, there is more demand for VM3. So there will be an increase in VM3 capacity, so which is shown by this image. So there is an increase in VM3 capacity. So how to handle this situation? There could be several solutions. So basically the scenario is with time, initially this is the VM3 demand, which was below this demand line, but after some period of time, in this period of time, there is an increase in VM3 capacity. So now you need more resource to accommodate VM3, right? And for machine 1, it is not possible to provide that resource. So what is the solution? So obviously the first solution is, option 1 is you can move VM2. You can move VM2 from machine 2 to machine 1. Like you can move VM2 from machine 2 to machine 1 and can place VM3 in machine 2. Can place VM3 to machine 2, right? So this is one solution. That is one option. Next option is you can turn on M3. You can turn M3 here. You can turn on M3, which was initially off, and move VM3 to M3. So you're moving VM3 to M3 and you don't need to move VM2 anywhere else, and no need to do anything with the VM1. So that is option 2. Now the option 3 is turn on M3 and move VM3 to M3. You can move VM3 to M3, move VM2 to M2 and switch off or turn off M2. So that is option 3. So there are 3 different options you may have to address this issue, right? So which one to pick? Which one is the better solution? How to decide that? So if you can look at this one, the option 1, here you have to move VM2 to some other machine. So there will be a migration cost. Say there will be a cost related to migration, which is say, and then you have to move VM3 to M2 also. Sorry. So you have to perform this migration 2 times. So this will be the cost. Here, you're switching on one machine and then moving. So there will be one migration cost and one as you are turning on this machine, new machine. So there will be a cost for that physical machine, say P. And for option 3, you are actually turn on M3. So there will be a cost to turn on a physical machine. Plus, you have to do a migration. So there will be a migration cost, M. Then again, you have to do another migration. So again, there will be another cost, M. Okay, so now looking at this solution, the costly solution is, of course, option 3. This one is the most costly solution. 2 migrations and 1 turn on of a machine. And again, there is another turn off, right? But when you're turning on one machine and turning off M2, so basically there will be another minus P because you're turning off one machine. So if these 2 things cancel out, what you can do, this solution is as same as this one. And then there is a solution where you have to perform migration and turn on of one machine. So now if by comparing these 2 factors, you can decide which one is the best solution. Okay. So there are different approaches of doing this server consolidation. This is a taxonomy that you can see for static and dynamic server consolidation methods which are used properly are exact method. Then there is the meta-heuristic method, and then there is the heuristics method. And in exact method, basically the stochastic programming, linear programming, non-linear programming, dynamic programming, game theory, etc. Different type of methodologies can be used to address this issue. For heuristic, you can think about the first fit, best fit decreasing, next fit, random fit, least full first. So different techniques like this heuristic. And in meta-heuristic, you can think about some approaches like genetic algorithms and colony optimization, particle swarm optimization, hybrid optimization, etc. And when you are doing this type of approaches, different parameters need to be decided. And different parameters are like hardware threshold, network traffic, migration overhead, reliability. These are several factors that need to be addressed here. For migration types, there are popularly 2 types of migration exist. One is the cold migration. The first one is the cold migration. In the cold migration, the services running on the server are suspended during the migration. So it will be suspended first, and then that means the VM is first stopped and then migrated. So after the migration, the VM needs to be started again on the destination server, which also takes some time lingering on the services running on the VM. On the other hand, in live migration, the static part which is not changing or having any active write operation of the VM is transferred first, while the VM keeps running on the source server. So it is actually running in the source server, and during the period of time, some portion which is static and not required for running in the source node will be transferred. And then after that transferring of that part, the VM is suspended and the remaining part is transferred. And in live migration, it reduces the downtime, because downtime is a very major factor for measuring the performance of the environment. So it reduces the downtime, but engages more resources for a longer period of time. So let's look at how the live VM migration happened in Google Compute Engine, in Google Compute Engine. So if you look at this figure, you can see that the first factor is the VM migration. Migration will be triggered. That is the first step. So if there is a migration triggered by a source task, or it will schedule the target task, right? And you can see that in the source node or the current running node, VM is running during this period of denoted by the green light here up to this. So here the source node will create a target task. That is the step 2. And after creating the target task, or during the period of time in the target node, it will set up a target VM. However, during this period of time, the VM is running. The VM is actually in the running state in the source machine. So next it will start migration, and when it is starting migration, after doing that authentication, it coordinates the VM migration. And during this period of coordination of VM migration, it will receive and restore the VM state. It will receive the VM migration state from this source task. Once this is transferred, it can resume that, and now the VM will be up in the target node, and target runs while the migrating stated. So here the source will stop its migration. Here the source will stop its migration, and it notified the completion. So it's completion, and after that, after the migration complete, it update the network. And here, after the updating the network, now the target task becomes visible. So the user can see that the VM is already migrated, and now the VM is running in the target node. So this is the period of time which you can say the brownout duration before the pre-migration, and this is the period which is known as the blackout duration. And during this period of time, there is no services provided from this VM. So that's why it is called blackout duration, and also known as the downtime. So different types of live VM migration. There are popularly 3 types of live migration. One is the pre-copy, then there is a post-copy, and hybrid. So looking at the pre-copy concept. So in the pre-copy concept, my first step is after starting the migration, it selects a destination server. The resource reservation will be performed at the destination site. It captures the VM, and it take the count of the dirty pages, and then iteratively copying the dirty pages to the VM to destination server. And so the scenario is stop and copy. If it is no, then it iteratively perform that task. Otherwise, it will suspend the VM running in the source node and transfer the VM state to the destination server. After that, it will resume the VM at the destination server. So to understand this concept, let's look at this pre-migration thing. So you can see that in host A, a guest VM is running. A VM is running, and this one is the destination host. So the first step is the pre-migrate step. In this period of time, the guest VM is running on host A, and it is live on A, denoted by this green line. So during this period of time, VM is live on A. which is combining pre-migrate and the reservation thing. So after this reservation, after the reservation phase, there will be a guest VM preparation on host B. But still the VM is running on host A. It is not running on host B. Next is pre-copy state. When it iteratively copy the states of that VM from the host A to host B, it is making the copy of VM from host A to host B. So it will there may be X number of rounds here, and during this period of time, the performance of the VM will be degraded on A. Okay, so after this pre-copy steps, there will be a downtime. So here you have the host A. So this is stop and copy phase, and in stop and copy phase, it is nothing but the downtime. So during this period of time, no VMs are running, not in host A, not in host B. Once it is done, during the commit stage, VM will be running in the host B. So now again the VM is live, but now it is live on B. And you don't need any VM in host A, so you can simply delete that image from host A. So this is how you can address the pre-copy thing. For post-copy, let me explain it from this figures. The first stage is the pre-migration state and the reservation state. In the pre-migration state, the VM is live on A. Then there is the reservation state. In the reservation state, you will get a copy of that guest VM in the host B. Then there is downtime. During this downtime, it's stop and copy. So guest VM will be stopped in this host A, and it will copy the rest of the part from host A to host B. And then after that, so this is during this downtime, no VM is actually running. After that, the page pushing round, if there is a page fault, the page will be pushed from host A to host B. After some number of rounds, so during this period of time, the server VM running on B will be degraded. After that, once it is committed during this period of time, it will be live on B. So you can see the downtime in pre-copy is more than the downtime in post-copy. So definitely the post-copy VM live migration is a better solution. You can also see here that here the downtime is this period of time, which is more in respect to downtime for the post-copy. So this period is less than this period, right? So you can see the post-copy is a better solution in respect to pre-copy. So in hybrid technique, it's a combination of pre-copy and post-copy both. It combines the different VM migration phases to improve the total migration time and service downtime here. So what are the different factors impacting the performance metrics over here? So the one very important factor here is the downtime. How to define this downtime? Because in this performance metric downtime, the major factors are the synchronization mechanism and low bandwidth network. So downtime can be defined as a downtime depends on the page dirty rate, which is denoted by So the downtime here denoted by the TD, which depends on the page dirty rate, denoted by D here, and the page size, which is L here, and the duration of the last pre-copy round, which is denoted by Tn, where N is the round N. So, and the whole thing will be divided by B, where B is the link speed. So by this, you will get the value of downtime, and in post copy, the downtime is less than downtime of pre-copy, and based on that, you can say the post copy mechanism is much better than the pre-copy mechanism. The next factor is amount of transfer data. It may be larger than the actual runtime data size because there must be some redundancy for synchronization and protocol requirement. So you need to define this amount of transfer data also. So when, I mean, at the beginning, when I is equals to 0, the transfer data is nothing but the memory of that virtual memory. So this is actually the amount of VM memory at the beginning. And then if you think about the TI minus 1, which is time taken to migrate the dirty memory pages during both in the pre-copy and post-copy techniques, that is generated during just previous round, is here multiplied by the dirty page rate. So this is how you can calculate the transfer data at the ith iteration. Next is the total migration time. Total migration time, if the large amount of data, for example, some pages need to be transferred multiple times because of modification, because VM probably running in the host machine, source host machine, and some pages may be modified during that time period of time, and then when you are transferring that pages, you may need to transfer multiple times. So total migration time is very important, and in total migration time you have to consider the total amount of memory that is denoted by VM that divided by the bandwidth. You will get the total migration time. So this is how you can calculate different factors which may impact the performance of the system. Besides this, there are other performance metrics like preparation time. That is the time difference between the initiation of migration and transferring the VM's state to the target server. And I mean, while you are continuing its execution and dirtying memory pages, then there is this resume time, which is nothing but the time migration is done, and resume is VM execution at the targeted server. So that is applicable for both the pre-copy and post-copy techniques. Then there is this application degradation. Due to migration of the performance of application is interrupted or slow down the services. So that is another factor which is very important. If the application degradation is not much, then it is good for that environment. Then there is this migration overhead, which is need of some extra machine resources to perform a migration, because migration may solve several issues, but at the same time, it also has its own overhead. So if you also need to consider that overhead part. If the overhead is very high in respect to the other achieved performance metrics, then probably migration is not a very good solution. But in most of the cases, if you can achieve other performances also, and migration cost is not very high, it could be a good solution. Performance overhead, degradation of the service performance during migration, like the downtime that we have discussed, or interrupting the service while executing smoothly, because during the migration you have to compromise with the performance of the application. So the migration process actually add several other things, like it may add delay, it may add some network overheads also. So these will also considered when you are when you are measuring the performance of that application. So the overall these things comes under the performance overhead. Then there is this factor of link speed. Sometimes the bandwidth is good, sometimes the network is good. Migration is not a very difficult in those situations. But if the network is not, if the bandwidth is not high speed, then there are a lot of issues with that. So the faster transfer requires more bandwidth, and a good solution is when uh, you don't need to spend more time as a downtime time, right? So these are some performance metrics that are considered here, along with the page dirty rate. If the page dirty rate is high, then it increases data sent per iterations, and it leads to the increasing migration time and the service downtime. And as I told you, service downtime is a very important factor over here, because service downtime is measuring the quality of the application. So if the downtime is high, it's not a very good solution. You need to think about some approaches where you can reduce the downtime as much as possible. Then if you are interested, you can also explore this VM live migration things using a Q emulator. QEMU is a very popular emulator and virtualizer where, with the help of the socket programming, you can easily visualize the working procedure of VM migration. So if you can, if you look at this particular flow diagram, you can see that there is one source node, there is one destination node, and in the source node, it is connecting a socket. After connecting a socket, so the idea is migrating VM from source to the destination. So first step is it sends some config, and after getting that, it can create a VM. So that means building a VM environment at the destination node. And then there are some steps inside node. It enables the log dirty. It will send the whole memory, etc. things, and then after doing that, it sends dirty memory pages iteratively. So this step is actually an iterative step, and during this period of time, it will receive this memory pages from the source node, and it receive them and restore them in the memory. Then there is a suspend time. Suspend time means after that, the VM will be suspended in the source node. So downtime will start from period. So you can see from here, downtime will start. VM downtime will start. And after this suspension, the source node will send data, dirty memory. It will send the VM context. Accordingly, the destination node will receive them. At the end of sending the VM context, it can save the Q emulated thing for future purpose if required. And then after getting all the dirty pages, destination can receive or start the QEMU and unpause the VM. So this is the period VM downtime as shown over here. After that, VM will be running in this destination node because migration is done. So the migration time will be treated from this beginning to up to this, and then the VM will be in the destination node. And after that, what you can do, you can simply destroy the VM over here, and before that, you can close the socket, because no more communication is required from between source and destination. So this is how you can emulate this virtual machine migration techniques using the QEMU or emulator and virtualizer for VM live migration. Next is a generic model of live VM migration. So the basic idea is what you can do here. You may have several type of servers, say server 1 to n number of servers, and in these servers, different virtual machines are running here that you can see. And from these virtual machines, what the first thing is, you have to collect the dirty rate measurement. So you are taking this dirty rate measurement over here. Then you are taking the page transmission rate controller, another module that will consider the page transmission rate. Then there is a model which is doing the prediction, a performance prediction model. And based on this performance prediction model, there is this migration decision, whether the migration is good or not, whether the migration will issue or not. So for this performance prediction model, you are taking the help of these two things, and with the help of this model, you are taking the decision of migration or not. So if there is a VM migration, again, it will update the logs and keeping that in the historical data of migration tests. So when you're doing this dirty rate measurement, you are actually taking the VM dirty pages tracking, which are online and running in these different servers, as well as you are taking the historical data. So you can see that the present scenario as well as the historical data. By analyzing that, you are deciding about the prediction model, and prediction model will help you to decide upon the migration decision. So this is how you can think about the generic model for the live VM migration. So I'm almost at the end of this lecture. Now I will discuss about some of the research challenges, which is very, general in terms. So the expectations here in this migration is it will be seamless to provide the continuous service, because hampering of service is not a very good thing. So user or the consumer demands the continuous services, and if the migration is there, it must be seamless so that it can provide that continuous service. But as we discussed this pre-copy, post-copy, live migration, different techniques, here we have one thing is very clear, that is downtime will be there. We cannot completely avoid downtime, but there will be some approaches through which we can reduce it, right, as much as possible. So that is one expectation. Another expectation is live migration moves this VM without disconnecting with the client. I mean, if the client is disconnected, that is also not a very good thing. So the expectation is there will be no disconnection with. Another expectation is performance of live VM migration must be very high for continuous services. However, these are the expectations, but in real scenario, the existing techniques or state of the techniques face many challenges while migrating memory and data intensive applications. Some of these challenges are like network faults, consumption of bandwidth and cloud resources, overloaded virtual machines. So these are actually the research challenges and need to be addressed by the efficient techniques, or think about some efficient techniques where you can where you can address these issues. Some common challenges that hamper live migration are also related with the transfer rate problem, or with the page resend problem, or the missing page problem. These things are associated with when we are transferring pages during the VM migration. And it depends upon the underlying network, it depends upon the resources, it depends upon the different factors, right? However, in most of the techniques, when we discussed about the VM migration, if it adds more complexity if it is over the WAN or wide area network. If the VM is migrated over LAN, then probably it bounded by that LAN network, the quality and performance of that LAN network. But if it is over WAN, the complexity or the challenges will be more. So these are actually the research challenges related with the migration and the server consolidation. Some other general research problems are like resource allocation, because cloud computing environment is representing a pool of resources, right? And this pool of resources are mainly the physical machines. So what we need is to think about a function. That function will provide a mapping of this virtual machines to the physical machines, right? So if you have this type of mapping, then that comes under the resource allocation problem. That is also important for VM scheduling problem. Then there is the fault tolerance techniques, different type of fault tolerance techniques. In fault tolerance techniques, you can think about the migration solution itself. You can think about the load balancing itself. whether it's a fault tolerance technique or load balancing, the migration is a very obvious option to handle these situations. But when you're doing the migration, you also need to think about the cost optimization, because when you're doing migration, you have to think about the cost of doing all these things. And in cost, different factors you have to consider. The cost function should be like of a function of the migration. It should be function of the network, and it should be function of the downtime. So these are some factors that you have to think about when you are considering the cost. So once you have this cost function, the objective is actually the minimizing minimizing the cost function, minimizing the C. See, that is the main objective here. And while you're doing minimizing the C, at the same time, you are actually want to improve or maximize the performance of you may want to improve the performance of the system. And when you're thinking about the performance, how you can define performance? It's nothing but the downtime. It's nothing but the downtime, right? So if the downtime is less, then the performance is better. Or you can think about the energy consumption. So these are different factors. So for downtime, you want to reduce it. You want to reduce it. For energy consumption, you want to reduce it. So again, these are the minimization functions. So it's not a single optimized function. It's a multi-objective problem, actually. That this is what I want to share with you. It's not a single objective function. It's a multi-objective function. And when you have a multi-objective function, you can think about some trade-off solutions. You can think about some heuristic approach to solve that issue. So usually this type of problems are NP-complete problems, but you can design some heuristic approach, heuristic solutions for addressing this type of problems. So as I told you, in trade-off, you have to think about this cost and performance factors mainly, as I discussed over here. You can think about a multi-objective function for making it a better trade-off among the cost and performance. So that's all. These are some references from where I have taken some information to prepare these slides. And there are some references done by my team of students. Here I would like to thank my PhD students, Binoy, and my colleague Shunirmal Khatua, Professor Shunirmal Khatua, Asif Iqbal Midda, and there is Srimoy Bhattacharya, and all the students who have been involved with me in this work. I would like to thank all of them. So thank you so much. Now I'm done.